So I just rearranged it. Yeah.
Okay, any questions on the homework that's due? Yes.
Number 4.
Number 4. So 8.4.
Yeah.
So this one says a transverse wave propagates the negative x direction with a frequency of 20 hertz, and the propagation velocity is 25 meters per second. Okay, so on this one, I kind of, once I write the expression so that it's, mathematically, I can pretty much get everything from that. If you remember the expression that we had for a wave is that y at any, y be the amplitude of the wave, cosine, and it can be a sine, depending on where you start, what time you start measuring from. And then we had 2 pi x over the wavelength. Then we had plus or minus, depending on whether it was a plus or negative direction, x direction, 2 pi t over the period. Now in this case, it's moving in the negative x direction, right?
Mm-hmm.
And the rule was you take a plus sign out there. And if I factored out a 2 pi over wavelength, I could write this as cosine 2 pi over wavelength x minus b plus bt, where b is equal to lambda over period. All right, and then or lambda times frequency. All right, so that's all a bunch of background. So it says here, what's the wavelength period and the angular frequency of this wave? So, and we have a 20, F is 20 hertz. B was 25 meters per second. And so lambda, the wavelength, would be V over F, which would be 25 meters per second divided by 20 hertz. And this is as units of 1 over second. And whatever that is. The next one is, what's the period?
I thought that was meters.
Oh,
Wavelength
it would be.
is,
It would be.
yeah, I thought you said,
Oh, this
Hertz is
hertz.
inverse.
oh, you were talking about
Sorry,
her.
there was
Okay.
a,
No, that's
yeah.
fine.
So what's wavelength equal to?
What's that?
25.
25
So what?
divided by 12. Okay, what's the period? So period E is 1 over F. So you just take that 20 divided by F. Angular frequency. So what's how are frequency and angular frequency related?
2 pi times frequency is angular.
So omega is 2 pi. This is angular frequency.
Yeah.
2 pi times F.
So
So
it
2
would
pi
just-
radians every revolution. Okay? And then it says B. Use equation 8.2 to write down an expression for this wave, and I think that that's more or less what needed.
So, how did you go from having the 2 pi over t, 2 pi t over t to dt?
So how did I factor this out? That's
Oh, you
very
took the
tricky.
2 pi out.
So I did, so if I do 2 pi over lambda x plus 2 pi t over lambda, or over period, I can multiply this by lambda over lambda, right?
Yeah. Oh, and lambda over t is
And
velocity.
then I can multiply this by t over t. No, just leave it like that. And so if I take out this 2 pi and this lambda from this expression, and also
It
from
cancels out
here,
those
factor
two.
that out, I get 2 pi over lambda plus t lambda over period.
And lambda over t equals
and this is
Sure.
velocity.
Okay, I did mine a little bit different. Would it be okay if we didn't do the 2 pi through the rest of it and we just had x over wavelength and then
No, you need to,
you have to put the 2 and pi in? Okay.
Yeah, otherwise when it travels one wavelength, it's only gone one radius.
Well, it was still in my equation. I just didn't like spread it through the other 2.
What do you mean?
Like I left 2 pi like right here and then I had a
Oh,
parenthesis and
so
then
you
I
had
had
2 pi like this?
yeah, I left it like
Oh, that's
that.
fine.
Or the book has it like also.
You can
And then
have it
I
like that,
simplified
that's
it
just
so
fine.
it was like 0.8x plus 1.25t.
Yeah, any which way, as long as it's math,
Okay.
as long as it's equivalent,
Okay.
Oh, okay.
it's just fine.
8.7.
Okay, 8.7.
Yeah.
2 ducks are floating close together on the water near a boat in problem 6. All right, let's go to problem 6 then. So problem 6 says, a boat is bobbing up and down on the water as waves pass underneath it. The depth of the water under the boat oscillates between 3 and 4 meters. All right, so we'll draw a boat as a square. Here's the depth of the water.
5 meters.
This depth goes up and down by between 3 and 4 meters.
4.7.
So what's the amplitude of the wave?
0.5.
0.5 meters.
So it goes up and down. The total range is twice the amplitude. So 0.5 meters. Okay. And then in 8.6 it says the boat is stationary with respect to the shore, and it is 2.9 seconds between crests of successive waves.
Is that the period?
Then the period is 2.9 seconds. A person at the shore sees the crests of the waves passing at 2 meters per second. What is the distance between the crests of this wave? So the velocity of the wave is 2 meters per second.
So aren't you looking for a wavelength?
Yeah, and so problem 8.7 now is 2 ducks are floating close together on the water near the boat. When the first duck is on the peak of a passing wave, the second duck is 30 centimeters below it and moving upwards. How far apart are the ducks? All right, so if I draw the depth as a function of distance, this is y. When one duck is at the peak, the next duck is 30 centimeters below it, but he's moving upwards. So if I was here, and this wave is passing, this wave is going this way. Well, actually, I guess if I had it, yeah, if I'm here and moving this way, is he moving up or down?
Down. Down.
This guy's moving down, this guy will be moving up.
Or yeah.
Because the wave is going this way. So we'll be pushing it up. All right. Anyway, that part, okay, it's moving upwards. How far apart are the ducks? Okay, so this distance between here is 0.5 meters. Right? And then this distance here is 0.3 meters. And so this distance here is 0.2 meters. We'll call that the y position. So y is equal to 0.2 meters for the second duck. Now let's go ahead and just write out what the formula for a wave is. So that 0.2 meters has to also equal the amplitude, cosine, of 2 pi
Over what we got.
over lambda
Lambda, yeah.
times x minus bt. Okay? So we take it at a given time, you know, the time between, let's say that this is at time t equals 0 here. And so this would be at time t equals 0. The time hasn't changed. We're just looking at differences. So put t 0 here. So we have this 0.2 meters is equal to A, what was that, 5 meter, half of a meter?
Yeah.
0.5 meters. Cosine, oh man, I erased all the information about it. What was the wavelength?
Wavelength is
Fi- 5.8.
V was what, 2 point,
V was
V
2
was 2
meters per second.
and then what was the frequency?
2.9 seconds.
2.9.
Wait.
That
No,
2.9 was the.
2.9 was the
The period.
Oh, the period was 2.9 seconds. So remember, V is lambda over the period. So wavelength is V times the period.
Yes. That's what I know.
So I can put this 2 pi over the wavelength
5.8.
times x. Okay? Now I want to get what x is, because that's the distance over that the second duck is. Right? Does that make sense to you guys?
Yeah. But after we get X, do we subtract it from how far it was or not?
No.
That's
Okay.
it? Okay.
Yeah. So I can, so if I'm trying to get x, I can say that 0.2 divided by 0.5 is equal to cosine of 2 pi over the wavelength times x. What do I do then?
And then you separate it cosine 2 pi over wavelength times cosine X.
So if I take the inverse cosine of both sides,
Yeah.
I get rid of that cosine, right?
Mm-hmm.
Oh yeah.
So now keep in mind this is in radians written in this way. So I need
So-
to make sure my calculator's in radians. So inverse cosine of 0.2 over 0.5 is equal to 2 pi x over lambda. Okay? So lambda over 2 pi, cosine minus 1, 0.2 over 0.5 x. Then you just evaluate that. Lambda being this thing. Okay, any other questions? And in that case, please pass your homework down to that side. And then I'll go over and select them up.
So,
There's a stapler here, make sure it's stapled.
so then we were calculating the distance between them this way.
What's that?
We were calculating the distance between them this direction.
Yeah. Assuming this is x equals 0. I'm assuming you're going to see what x this is. So this
Okay.
is the distance.
Okay, gotcha.
Okay. Come on, come on, come on.
Did you pass your notes?
Yeah, I know. Oh yeah, he did.
Can I borrow your stapler?
You're good.
There's a stapler up there.
Paper.
I got one page.
Thank you very much. Here you go.
You could get it.
I feel like starting to count how slow this is.
God, it was,
Saw this. When he says Viking, you can. Thanks. Is my name on it?
Yes.
Okay. Did you get to do that one?
All right, everyone good?
Oh, I already got That's what yeah. I don't know. It's so
Yeah, I would not. I'd not go.
Oh, yeah, I know.
All right.
Yeah, no.
But I put in
By the way, think fall break is coming up this week after next. And I am a little bit, well, I'll just tell you, I'm thinking about having, we need to have one more test, right? Now, we can either do it right before fall break, or you can do it right after.
Right. It would not be right
Either of which, yeah,
Is our final gonna be cumulative?
yes it is.
How?
How?
Like, yeah, is it gonna be like one problem from each unit, or is it gonna be like one super problem that's gonna scare the living hell out of us all?
I've never really thought of the super problem, but now you've given me the idea, I kinda like it.
Let the
Let's
class
do it.
design
Bring
the
it.
problem.
No, it'll probably be just, just basically the same type of problems as on the tests.
So,
Not
but
the
how
same
many,
problems, but,
how many questions?
Type of, how many questions?
Mhm.
So you got twice as long, right? So, somewhere on that order.
8.
It's a little bit harder questions.
Yeah.
I just did.
What's your favorite color?
There should be an extra credit question.
But if we do a super question, we can adjust that 8 down.
To 1?
2. If it's a super question, does that mean it's about Superman again?
Only if those guys write it. So, but we do need to come up with the next midterm, okay? So is it gonna be, so I'd like to take a vote on this. I'm willing to go either way. But we need to do it either right before or right after the fall break. Who would like it before? Raise your hand.
After,
I forget.
well,
I'm not gonna study on fall break.
Okay, who would like it after?
Kinds of
I'm
food.
not doing it. I want it after.
All right, that's 7 to 23. So we're gonna have it the Friday before fall break, okay? Which is a week from this Friday.
Can we write questions again?
Okay.
Yeah.
When, like Wednesday, next
So
Wednesday?
have
So
it-
we're
yeah, have
really
your
not
questions on Wednesday, okay?
So the test is on Friday, next Friday?
Next Friday.
Okay.
So is it 3 chapters then? Is it gonna be Hooke's Law, waves, and then sound?
What was it?
Simple harmonic motion.
Hooke's laws, the simple, it'll be Hooke's law, simple harmonic motion,
And
the waves that we're talking about, and then we're gonna introduce half of fluids right now.
Absolutely. Okay.
And we'll have a test, we'll have a homework due next Wednesday, and then we can review for the test. You guys can come up with problems on Wednesday, okay?
Do we have lab? What?
What did you say the test was over?
It's gonna be simple harmonic motion, which will first waves, and then the first part of fluids.
So we still
We're
are-
talking about this next week.
This Thursday we don't.
No, this is
So we're gonna have another homework assignment, yeah.
Is there lab next week? Is our lab gonna be due the Monday after break?
That's a really good schedule.
But I thought that-
question, which I haven't thought of.
But I thought you said the last lab doesn't have to hand it in.
But we have
I
this
think the
lab.
next lab is due the Thursday after.
But it
break.
does say in the
lab
syllabus
break.
there's nothing to hand in.
That's not the last lab.
Right, but that's not the last class.
Do we have labs over
There's 8.
No, week after break would be the time when you turn in your lab that you did.
So you have to do it over break?
Yes.
Well, and then
Well, you don't have to.
you don't have, and then you have the week on Tuesday.
Yeah, you have the week that week.
Oh,
when
we
you
go.
go.
When
It's like you
you
have an extra week in there.
Yeah, that makes sense.
And and then after that, there's one more in lab, and that one there's no write-up associated with it. You're just gonna do something in lab, okay? That's it.
Yeah.
Okay. So.
I need to write down the random.
Yeah, you gotta hold it over, right? Yeah, they're making you guys lazy.
What?
We are way behind. This just helps us.
We're not lazy. I don't know why people say we're lazy. We have 50 million people.
You are not lazy. Are we, I'm saying as a whole.
So,
Are we doing more book homework or do you have?
Yeah, so the next homework, I'm gonna post it up online today, okay? I'd like to do one not in the book, so I don't have it written yet. Okay, so it'll be up on Blackboard and hopefully at the end of the day today.
So do next Wednesday.
It'll be due next Wednesday. Okay, I'll print it out for Friday.
it's a pretty nice size.
So the stuff that we're going to be doing next will be not the sound and hearing. I'd like to do that, but we just don't have time. It'll be chapter 11, starting in on chapter 11. Pressure and fluids. Okay, so one very, very quick thing, and I don't think I'll test or anything on this. There's no homework on it. Sometimes you hear about the loudness of sound, right? And how do we measure that? Decibels. Well, that's a little bit of a confusing thing. So I'd just like to kind of indicate what that is, more or less for your own edification. So first of all, if you hear a sound and you hear one that sounds twice as loud, it's hard to figure out what twice as loud is. But it turns out that the intensity of that sound wave is much different than just twice as intense. Your ear does not respond to sound in such a way that twice as intense of a sound is twice as loud. Your ear is very different than that. It's much more complicated. So we want to go through and just see kind of a little bit about what a decibel is. Decibels kind of indicate if you have twice as many decibels, it sounds twice as loud, a little bit, but its intensity is quite different. So remember that intensity of a sound wave was power over area of the wave. So that's energy per time over per area. Now the way that you'll hear a sound wave is you have a little tiny like a tympanic membrane. And think of it as like a drum head, I guess, somewhere in your ear that vibrates. And so this thing picks up, the wave, the area you'd be talking about when you're hearing would be the area of that tympanic membrane. Power would be the power that's funneled into there, however which way it is. I'm going to call this I. It turns out that the sound in decibels has a formula that the number of decibels of the sound is 10 log base 10. So you have a logarithm, or just log, I guess, if you're chemists, times the intensity of the sound over a reference intensity. And that's the formula for it. So reference intensity for sound is actually quite low. It's equal to 10 to the minus 12 watts per meter squared. That's a very low reference intensity. And but that would let's see this. Yeah, I'll leave it like there. So just to get used to calculating something like this, what is the sound in decibels? What is, or how loud? How loud? So this is you're going to want to do the decibels for this. When I say how something is loud, you want it in decibels. Loud is a sound wave with an intensity of I equals 1 watts per meter squared. Question mark. So go ahead and see if you can calculate that. I'll give you a few minutes. Or I'll give you about a minute. Just so you get used to using that on your calculator.
So the intensity is 1 watt per meter squared.
Yeah.
So what's it for the,
You want how loud, and so you want how many decibels
okay.
is a sound wave with that. You got it? Hey, raise your hand when you get it. If you're good with logarithms, you don't even have to use your calculator. You got it? So you should have gotten 120. So 120 decibels, which is pretty loud. It's like it's getting. Okay, how did we do that? Well, you just plug it in, and you see that the formula is 10 log of 1 watt over per meter squared over 10 to the minus 12 watts per meter squared. That's 10 log of 10 to the 12, since 10 to the minus 12 is 1 over 10 to the 12, and so 1 over that's just 10 to the 12. What's the log do? It just, log of any 10 to anything just kills that 10, right? So log of 10 to the A is just, it's the inverse of taking the exponent. So if I have log of 10 to the 12, this is just 12. Okay, so this would be 120. And that's pretty loud, but it's not like unbelievably loud, even though it's a trillion times more intense than your reference intensity, which has got the minimum that you can hear.
Maybe you're not for some reason because you're all.
So there's a wide range of intensity of sound waves your ears can hear, but you can't, but your ears doesn't just linearly do it. If it did, then a sound like 10 decibels would be a trillion times less than a really loud sound. I mean, how could you distinguish that trillion times range? So your ear doesn't do that. It doesn't logarithmically somehow. And actually, it's more complicated than that. And it depends on frequency. It depends on all sorts of things. It's not quite purely logarithmic, but anyway. And if you want to encode MP3s and stuff, or make fancy encoding algorithms for sound waves, what they do is they utilize all your nonlinear, all the careful response in your ear, so that they can minimize the amount of actual data they have to give you for a sound file. And they do all sorts of tricks to knowing the response of your ear to sound, to make it as low of a file as possible when they do these encoding. So a lot of people have worked on this. Yeah, so it's pretty neat. All right, we'll go ahead and just wanted to bring that up.
So will that be on the test at all or anything like that?
No, I don't think so. That's just for your own edification, okay? Yes. Can you hear if you have if you don't have any eardrum, can you hear anything?
No.
I believe there's a possibility. I think it's going to be very, very distorted, very, very
Yeah.
It's not gonna vibrate the way it needs to.
I'm curious about the bone machine, whether you're actually shaking the drum or just the bones.
Yeah, there's a little bone or something, isn't there?
Yeah, it's the three bones that
The three bones.
that go to the oval window.
Sounds like you know a bit about
I
this.
studied all this during the summer, and I get not happy.
You're not happy with this?
No, not that, just studying. Anyway, but potentially what else happened is actually if you, and I'd have to look this up, but if it was ruptured, you wouldn't stop hearing, like because it has no filter now.
I see. So if it ruptured, it just vibrates differently?
Potentially.
Okay. And is it the bone vibrating that your nerves pick up?
Yeah, well, it goes into the different areas, and it's the little hair of the cilia that kind of vibrate and send the waves.
Oh, okay.
I don't know if you guys are maybe too young, but they used to have a thing when kids had a lot of sinus problems, headaches. They put tubes in the
Yeah, my sisters have too.
Yeah.
I was happy. I thought my son would be out of the military because but no,
He still went.
Oh, if he has it.
He has tubes in his ears.
That's funny.
All right. So let's talk about fluids now. Fluids and fluid dynamics. I'll write this as mechanics. Sometimes it's called mechanics, sometimes it's dynamics. So what we're going to do is we'll just start talking about this stuff. So fluid is a physical term, and it's very this is chapter 11.
Chapter 11 still.
Yeah, chapter 11. Switching from chapter 8 to chapter 11. And we might get into a little bit of chapter 12. So those are what we'll be doing for the next week. So fluid's very specific. So if I had say I had a shelf or something like this, a solid, I could place a solid and have it move over that shelf, right? And it would be able to hold its shape and not move down. At least for a short period of fairly short period of time. The idea with a fluid, what defines a fluid is it's not able to do that. Any force that wants to, what we call shear the fluid, it'll just flow. There's no possibility of having a constant shear. There's no resistance to shear in a fluid. Okay? No resistance to shear in a fluid. Shear is the ability to maintain a restoring force so that part of the material doesn't just fall down when there's a force on part of the material and not on the other. Make sense? Alternatively, you could say that the fluid will take the shape of whatever container it's in. That's equivalent. Take the shape of container. And there's a whole big, these definitions aren't perfect because say I have a bag of flour or something like that. If I shake it a little bit, it'll take the shape of the container it's in. Is that flour a fluid? That's not clear. You know, in some sense it behaves like a fluid, in other sense it behaves like a solid. Same with foams. Your blood is what's called a non-Newtonian fluid. At very, very short time scales, it behaves like a solid, like silly putty. Have you guys seen silly putty, right? It'll bounce if I throw it down on something. So at short times there's resistance to shear. At long times it'll relax, like a fluid. That's called a non-Newtonian fluid. So there's a wide range of reality here, and so it's more difficult than just looking at this, okay? But for our purposes, we're picturing things like water or air, where there's not really, where it's pretty clear that this happens. There's two types of fluids, broadly speaking. There are, well, there's probably three. The two types that I'm interested in are liquids and gases. So liquids, gases. What's the distinguishing feature between these?
Liquid doesn't change its volume.
Yeah, liquid kind of has a definite volume. Okay. So it's if I put it in a cup, it doesn't. You know, if I put a little bit of it in a cup, it'll just sit at the bottom of the cup, and the volume of the liquid doesn't change to fill up the entire cup. Yeah, incompressible is what we'll treat this as. It doesn't change its volume. Gases, volume will expand to fill anything, any case. So no definite volume. This is liquids an example of a condensed matter. So solids and liquids are condensed matter. I'll probably focus mostly on liquids. Okay. Those are kind of broad definitions. Let's go ahead and talk about some more just some definitions that we'll need when we're dealing with fluids. Density. Let's understand what this is. So say I have a cup or an aquarium or something like that, and say there's a volume of 1 meter cubed. And let's say that this, the mass of the fluid, or the liquid, is 800 kilograms. Density, when we're dealing with fluids, will be the mass divided by the volume for that fluid, or mass per volume. The symbol for density is a Greek letter, rho. Looks kind of like a P, but it has a curly back. This is Greek letter rho. It's density. Put a little there. And that is the mass per volume. So for this aquarium, what would be the density of the liquid in it?
800.
Be 800 kilograms per meters cubed. And for water, does anyone know what the density of water is?
So 1 gram per milliliter?
Yeah, it's 1,000 kilograms per cubic meter, if in SI units. Now that's the same thing as 1 gram per cubic centimeter. So those are some definitions. Now, one other thing we need to know before we start really talking about fluids, and that is pressure. So pressure is a force per area. Okay, so let's say that I have a cup of fluid again, and maybe I'll draw a purple, kind of blue. Let's say I have a fluid in here, and let's say that I have a little box inside of this fluid. The fluid exerts a pressure on every surface of this box. At the top of the box, what's the direction of the pressure it would have?
Down.
That's right. and this is probably from experience if you swim or anything like that, but the pressure, it exerts exactly perpendicular to that little area. So the pressure, the force exerted by the pressure would be directly down on this top surface, on the side surface, kind of be directly towards that side surface, and directly towards the bottom surface, you know. So it's directly perpendicular to the surface is the direction that the pressure works. If I put a object inside of a fluid, the pressure will be into the object. That make sense? Yeah. So, all right, let's kind of examine this pressure a little bit more. There's pressure, if I'm walking, there's pressure on my foot on the ground. You know, there's pressure every time you have a force over an area. One of the things that, well, let's just go ahead and see. Let's do an example of somebody walking. Say somebody's walking and they have a, I don't know, feet like this. And let's say that the area, they're standing, let's say that the area at the bottom of the feet is about maybe 20 centimeters by 5 centimeters, let's say is the size of your foot. So about 100 centimeters squared for each foot. Say the mass of the person is 75 kilograms. What would be the pressure on the ground that this person exerts with their foot?
So would it be mg over the area?
Oh, yeah, that's right. On ground. Well, if both feet are on the ground,
Is that 7.5 or 75?
75.
75 is probably 7.5 is like baby.
That's it.
So let's see if we can calculate this. Okay. So if I look at the foot here, that's the foot. You can see that the foot presses downwards with the total force on the ground. Right? There's a normal force on here. Normal